kind of about like what are the theory behind NMR spectroscopy. Remember what happened is you have your nuclei being responsive as little magnet to an external magnetic field. And then the neighboring atom will shield your target signal from that magnetic field to give you special NMR spectrum. So in the NMR spectrum, using the proton NMR spectrum of ethanol as an example here, we covered 4 different kinds of information you can get by reading the NMR spectrum and how to understand them. Right? So the first piece of information is a chemical shift or the position of your peak on the proton NMR. And that tells you the relative environment your target signal or target nuclei is feeling. Or number of peaks tells you the number of chemically inequivalent nuclei or hydrogen you have in your molecule. Integral of the peak, that tells you information about what's the relative ratio between different types of hydrogen atoms. And then also the splitting pattern, which tells you how many neighboring hydrogen atoms you have in that molecule. So using that 4 pieces of information, we can eventually derive the molecular structure of an organic molecule. So we haven't got the chance to actually derive these spectrum on top of ethanol. So we'll do 2 examples here together and see how to read your NMR spectrum and get information about the molecular structure. Ready? Let's get started. And once we finish that, we'll jump into the different spectroscopy methods. The first example here is one type of question you might expect is we give you the molecular structure, which in this case is a 1,1-dichloroethane. At the same time, we also give you the NMR spectrum. What you might be asked doing, this one is more or less the easier or the straightforward question you could expect, is now how do you assign the peaks onto this known chemical structure? Now we know the structure looks like this, right? What does these peaks corresponding to? So if you think about it, we have 2 different peaks, and in my molecular structure of the 1,1-dichloroethane, we have 2 different kind of hydrogens, or 2 different types of chemically inequivalent hydrogen atoms. If I draw it out in green and in blue. Right, now we look at it. There are several pieces of information you can get in order to help you in assigning these peaks to the specific hydrogen. For example, we can use the integral. We look at the integral, we realize that my peak B, the ratio to peak, from peak B to peak A is about 1:3. Right, so if we're talking about the kind of hydrogens corresponding to my peak B, which is here, to the hydrogen that's corresponding to my peak A, it's about 1:3. So that's corresponding to say, hey, my peak B is likely to be my green hydrogen, and my peak A is my blue hydrogen. So you can use the integral. You can also use the chemical shift, or delta ppm here. If you think about it, when we're having our peak A here, this one is more shielded. It's closer to our TMS reference. While our peak B here, it is more de-shielded. So if you're comparing these 2, for one, my peak A has more nuclei around it to shield it from the environment. So peak A is more shielded. Or it is more upfield. So that's corresponding to my CH3 group here. While my peak B is more de-shielded by the electron-negative chlorine atoms around it. So the chemical shift also tells us that my peak A is my methyl group, my CH3. My peak B is the hydrogen attached to the carbon with the 2-chlorine. All right? And then the splitting pattern. Splitting pattern is also telling us the same information. So if we look at this hydrogen here in peak A, this one is a doublet. Or what the doublet means is we have one neighbor hydrogen, which is my hydrogen on the carbon with 2-chlorine, just one green hydrogen, making that a doublet splitting pattern. Alternatively, if we're looking at peak B here, this one is a quartet. And a quartet means you have 4 different signals, right? And using the N+1 rule, we know we have 3 neighbors. Neighboring hydrogen. And that's 3 neighboring hydrogen coming from my methyl group, having 3 hydrogen around it. So this is a very good example. Is by reading the NMR spectrum, you'll figure out these pieces of information would frequently work along with each other. As you can get the same kind of information by looking at the spectrum, and they're all hinting towards the same molecular structure. Yes?
Just to clarify, is the short peak, is that the H attached to the 2 COs?
This one?
Yeah.
This one is the green peak. That's the green one. It's a hydrogen attached to the carbon with 2-chlorine.
Are the 3 neighbors as a carbon and 2 chlorine?
So when we're talking about neighboring, we're not talking about neighbor carbon. We're talking about the hydrogen that are on its neighboring. So this is a carbon, this is a green peak we're talking about. It is a quartet. And adjacent to this carbon atom, we have this methyl group. And on this methyl carbon, we have 3 hydrogen atoms to shield this green hydrogen. So that is why this peak B, which is a signal corresponding to the green hydrogen, is a quartet. Yes?
I actually think like the 1-to-3 ratio, so the B to A.
This one will be given. This one I'll just give you what the integral is. Again, this is not a calculus class. I don't expect you to do the integral by hand. Yes?
And the reason why you know that the carbon with the 3 H's is more de-shielded and
This one is more shielded. So the CH3 group, this one is the primary primary alkyl group. If you remember our trend, the primary alkyl group is more shielded and it's closer to my reference TMS.
so I guess my question is how do you determine like which peaks correspond to what on the actual molecule?
That's what we're doing here. We have 3 pieces of information here. We're trying to assign the peaks into the hydrogen atom in the molecule. Right? You can use all 3 kind of information. You can use the chemical shift. That is looking at whether or not on that same carbon you have electron negative atom attached to it. Or on that same carbon, do you have hydrogen atom attached to it? If you have hydrogen atom on that same carbon attached to it, those hydrogen nuclei will shield your target signal. So that's why our blue peaks are more shielded. More shielded means it's more upfield. It has a smaller ppm number. If you have electron negative atom attached to the same carbon, it will withdraw electron density from that carbon and de-shield that hydrogen, making it more downfield shifting. Or you can use other information. You can use integral or splitting pattern that's telling you the same kind of information. All right, so this is, I would say this one is one of your fundamental skill you need to know. If you're gonna know anything, how to assign peaks in your NMR spectrum, that's definitely one thing you need to know from this class. So let's look at another example and see what are my other ways to ask questions of NMR spectroscopy. So let's jump into my second example, which is, for example, I give you the molecular structure. And now you look at it, can you tell me how many peaks do you expect and what are the splitting pattern of those peaks. So now let's look at it. How many different peaks are in there? That depends on how many chemically inequivalent hydrogens do we have. So my OH will be one of it. It's going to be it's an OH. It's one of your special case. This one, you're expecting it to be a broad singlet. And the chemical shift of this OH peak varies from 0.5 to 5.0 ppm. And again, when we're assigning the chemical shift of these groups, I don't expect you to know the number. It's open book. You can check any chemical shift table, but just know the relative trend and which one of the group is more de-shielded comparing to the other. That's as far as I want you to know. It's more of the qualitative comparison of the peaks. And let's move on to look at these hydrogens. This one has a CH2. So this one obviously will be different comparing to my OH. It has different connectivity. And what is the splitting pattern of this green peak? That depends on its neighbor. We don't count OH as its neighbor, but here we have two more hydrogen that are neighboring to my green hydrogen. So that means my green hydrogen, we're expecting it to be a triplet. My red hydrogen also have two neighbors, so we're also expecting them to be triplet. These two groups have very similar chemical environment, so we're expecting their chemical shift to be pretty similar to each other. All right, so that's already 3 peaks. And now let's move on to our benzene ring. So again, remember when we were talking about chemical equivalence, the distance towards that oxygen, towards that functional group is important. So these two are my ortho hydrogen. These two hydrogens are chemically equivalent to each other. And what are their splitting pattern? Well, that depends on how many hydrogens do I have on the carbon adjacent to my purple or to my pink hydrogen. So that's on my meta position. So around each of my pink hydrogen, we have on the carbon neighboring to that pink carbon, we have one hydrogen attached to it. So we're expecting these ortho CH to be doublet. They are chemically equivalent, so they will show up in one single peak. And what about my orange one? My orange one, these two are chemically equivalent. What kind of splitting pattern do we expect? So here we have our para hydrogen, that's in purple. So for each of my orange hydrogen, it has two neighboring hydrogens. Both the ortho and the para hydrogen are the neighbor to my orange hydrogen here. So with two neighbors, we're saying that's a triplet. And my para hydrogen here will also be a triplet. All right, I'm just gonna quickly write my para here for you if you don't remember. So para, meta, ortho. All right? With me so far, that's how you assign the splitting pattern. And let me do one more thing before I take questions. So now if we're talking about the relative integral of these peaks, what are their relative integral? We can leave the OH aside. We don't care too much about the OH integral because that's not accurate. The green one, we have 2. Here we have 2 because we have 2 hydrogens associated to it. The pink one also have 2. The orange one is 2. And at the end, our para one is 1. So 2 to 2 to 2 to 2, 1. And here, the green one is a triplet. The red one is a triplet. The pink one is a doublet. And the orange one is a triplet. And the dark purple one is a triplet. So by just simply looking at the structure of an organic molecule, you can already picture what your proton NMR looks like. And now if you have the actual NMR, it will be much easier for you to actually assign the peaks to specific hydrogens. All right, this is the second way we can ask questions about, is we give you the molecular structure and ask you to give us some information to predict what the proton NMR looks like. You don't need to tell me what are the actual chemical shifts they are, but the relative position of those chemical shifts, that's something that might be asked. But you can check the table for that. But splitting pattern and also the number of peaks, or predict the integral, predict the ratio by looking at number of equivalent hydrogens, that's something that's fair. Okay, questions? Yes.
Okay, how does the H and the OH not count for the green hydrogen?
Right. So here the OH is special. OH, NH2 at the terminal, and also SH, these are all special. And the reason they're special is something we did not cover. They are frequently involved in hydrogen bonding with the solvent, so they might not be around to shield your neighboring hydrogens. So that's why I always single out OH, NH2, and also your SH. So they are just special things. Okay, more questions? Yes? So they will be included in the number of peaks. They will show up as your number of peaks. They do not contribute to the splitting pattern of the hydrogen neighboring to them. Yes?
So, yeah, how are the ortho and the meta hydrogens approaching each other since the overall molecule is not symmetrical?
So this one, when we're looking at this molecule, again, this bond, you can rotate it. So the rotation of this single bond makes your ortho CH equivalent to each other and the meta CH equivalent to each other. That benzene ring can undergo free rotation. All right? So this is the second type of question you're expected to know. It's given a molecular formula. Can you predict what those peaks looks like? And let's look at the third one. Or do you want to do one more example on this kind of question? Okay, so let's do one more example on this kind of question, and then let's look at the most challenging problem you would expect. So, imagine we have a molecule that we're seeing at the beginning of this slide, which is, well, let's see, that one is already used. Okay, let me just draw something randomly. Quite randomly, we're just drawing that molecule. And again, let's do the same kind of analysis and try to first get an idea about how many peaks we're expecting and what are the splitting pattern of those peaks. So get started. I always get started with the special one, which is my OH. So this one, we're expecting it to be a singlet, but and then let's move on throughout this ring. The next one here, we have 2 hydrogen attached to it. And then here on its neighbor, we have another 2 hydrogen attached to it. So the red one will be a triplet. Yeah. Two hydrogen hydrogen. All right, so the reason this one is a triplet is you have the two green hydrogen acting as its neighbor. Next up, if we look at this green hydrogen, now you have more neighbor than the red one, because here you have two more hydrogen. And let's write out the pink one. So this one will be a quintet, or 5 peaks. And the reason the green hydrogen is a quintet with 5 peaks is because it has 4 neighboring hydrogens, the 2 pink hydrogen plus the 2 red hydrogen. For the pink hydrogen, this carbon is already tetrahedral. It doesn't have any hydrogen around it. So my pink hydrogen will also be a triplet. And the reason it's triplet is because of the 2 hydrogen that's neighboring to it, the 2 green one that's neighboring to it. All right. And what about these methyl groups? These methyl groups are equivalent to each other. They're just 2 methyl groups attached to the same carbon. And along this 2 methyl group, here we don't have any hydrogen attached to it. That's the neighboring carbon we're talking about. So they are singlet. So no neighbor. And then we move on to these 2 hydrogens on the alkene. And I think I'm running out of color, so let me choose something else. Let's say a purple one and maybe a gray one. So for the purple one, it has only one neighbor that's on this carbon, which is the gray hydrogen. So this one will be a doublet. The gray one at the same time has one neighbor, which is the purple one. So it is a doublet. All right. And at the end, we have this CH3 group here, where it doesn't have any neighboring hydrogen. So this one will be a singlet. With me so far? So it's not hard. You write out all the hydrogen atoms, and you're just counting the number of neighbors each of these hydrogen have, and then you apply apply the splitting pattern accordingly. Yes.
Why does the CH3, why did the hydrogens in that, why did it not contribute as a neighbor?
Well, so these hydrogens are equivalent to each other. When they are equivalent to each other, they act as a single peak. So they will shield each other, yes, but that shielding is already taking consideration in that internal shielding. It doesn't appear as a splitting pattern.
Oh, sorry, I have really more questions. Then why in the three pair top, the pink, green, and red, why does it have 5?
Well, each of your hydrogen here have 4 neighbors.
Oh, and that one.
All right? How are we feeling about this kind of question? So you can take any molecule you have in mind, right, and just start practicing it. Just draw out the number of hydrogen atoms and start practicing it. And also you can get information about the relative size of the peak, area under the peak, right? For example, this one, we're expecting it to be a much larger peak because we have 6 hydrogen corresponding to it. So for example, if I'm asking you the question, what is the integral ratio for this hydrogen versus maybe this hydrogen here? You should be able to say, hey, that's 3:1, because it's 6:2 and we reduce it to 3:1. Or between this hydrogen here, the purple one, and this one, you can say that's a 6:1 ratio. Yes?
I have a question. So if the red hydrogen, where there's 2 hydrogens,
So when we're talking about splitting pattern, we're always looking at its neighbor. We're not looking at itself, all right? So this is a little bit counterintuitive, I know that. When we're talking about splitting pattern, you look at the carbon adjacent to that carbon center, and you count the number of hydrogen atoms attached to the adjacent carbon centers. All right? Okay. So that's the second type of questions we can ask. The first type is we give you the spectrum, we give you the molecular structure, and you mix-match these peaks with each other. Second type of question we can ask is we give you the molecular structure, and we're asking you to predict what the proton NMR looks like, what's the splitting pattern, how many signals do we expect. And the third kind of question is the hardest question of all. You're expecting at most one problem of that on your exams. So that's using the NMR spectrum and trying to derive what is my molecular structure. What does my molecular structure looks like? So this kind of question will give you more information in either molecular formula or after we learn mass spectrometry and IR spectroscopy, you'll also get information from those methods. But for now, let's just think about it. We have the molecular formula of C5, H10, and, well, oxygen. And in this molecule, we're trying to figure out, all right, what does my molecule looks like? So the first thing first you can look at it is something you can get by looking in your, that's something you can get in your 14A and B that you should learn, which is the level of saturation. So if you count the ratio between your carbon and hydrogen or your single bond, you can get how many double bonds do I have in this molecule. And by looking at it, we can say, okay, so 1:2 ratio, so we have one double bond in my molecule. And then let's think about it. So here, what we have on my proton NMR, so these two are just the zoom out version of the two peaks we have. We have a total of only 2 peaks. So what does that tell us? That tells us our molecule, although we have 10 hydrogen atoms, our molecule only have 2 different types of hydrogen atoms that are not chemically equivalent to each other. All right, so we are only having 2 different types of hydrogen atoms that are not chemically equivalent to each other. So this is telling us our molecule is a relatively symmetric molecule, if you have that in mind, because my hydrogen atoms are pretty equivalent to each other. And then we look at our chemical shift and the splitting pattern. There are different ways to do it. I'm just showing you what I would approach it from. So the way I would approach it is I look at the peak that is more shielded. So this one is a triplet. And that's the same peak here. That's the same peak that's more shielded. It has 2 neighboring hydrogens. So each of the nuclei in my triplet peak has 2 neighboring hydrogens. And then if I look at the peak that's more shielded, what we have, this one is a quartet. Again, when we're looking at whether it's a quartet, we count the peak here, right? 1, 2, 3, 4. It makes it a quartet. So what a quartet tells us, we have 3 neighboring hydrogens. So now it becomes quite straightforward. For this peak, you have 2 neighboring hydrogens. For this peak, you have 3 neighboring hydrogens. So if I write it out, they are neighbors to each other. We only have 2 peaks in my molecule. What we have is like I don't have enough space, a carbon with 3 hydrogen that is neighboring to a carbon with 2 hydrogen. All right, with me so far? So for the hydrogen in my more shielded red peak, it has 2 neighbors that's coming from my blue peak, and vice versa. So the 3 hydrogen in my methyl group are shielding my CH2. All right? So this also, we can also double check our logic when we're doing this kind of molecule building. You can check the integral here. So when we're looking at the integral, it's given 33 to 48, so that's about 2 to 3. It's not exact, but it's about 2 to 3 when we're comparing these two integrals. And in here, indeed, for the blue hydrogen, we have 2 of them, and the red hydrogen, we have 3 of them. But obviously, this is not the end, right? Our molecule, we have a carbon, we have more carbon, more hydrogen, also an oxygen in there. So how do we finish it up? Now we think about that carbon. So this CH, the blue CH, only have 3 neighbors that's coming from the methyl group. So that's telling me, although we have a carbon around it, this carbon doesn't have any hydrogen attached to it. And we know this molecule has 1 double bond. So it must be making a double bond with the oxygen. And on the right-hand side, we have the chemically equivalent molecules. All right? So that calls to the end of our entire molecule. That's giving us the proton NMR like we see here. It is a ketone with the carbonyl group right in the middle. At the end, you can always use a chemical shift as a sanity check. We have so many information in my spectrum, you can always check it up. If you think about it, my blue peaks are more deshielded comparing to my red peak. And one of the reasons my blue peak is more deshielded is it's attached to a carbonyl group. If you check the table, you'll see ketones, the CH2 attached to a ketone group will have chemical shift around 2.1 to 2.6, which is right in the middle here. So doing proton NMR to derive the molecular structure, that's one of the challenging problems you'll be having. You're putting those puzzles together to make the full picture of your molecular structure. How are we feeling here? All right. Any questions before we move on to IR spectroscopy? Yes.
Does the placement of the double bond of the O doesn't make the hydrogen on top, hydrogen on bottom chemically equivalent?
Now, if you think about it, we're drawing the Kokila formula, but if you draw the zigzag formula, what does this molecule look like? So your hydrogen are not on top or below it. It's in and out from that plane that's defined by the carbonyl group. So this is what the actual molecule looks like. And these hydrogens, whether it's in plane or out of plane, they are equivalent to each other. Yes? So 1 double bond, we're just looking at the level of unsaturation in your molecule. So for example, if we have ethane, right? So C2H6. So the number of hydrogen is 2 times the number of carbon plus 2. So that's 0 level of unsaturation. So that's something that's covered before. Yes? The formula will be given. Otherwise, you can get the formula by looking at mass spectrometry or like IR spectroscopy. So the question will give you the molecular formula some way.
For to get the saturation, if we did not have that 114.
Oh, okay. So raise your hand if you don't know how to calculate the level of unsaturation. Okay, we'll do that on Friday. That's unexpected, but we'll do that on Friday. Okay, that's something new. Okay, we'll do that on Friday. Any other questions? Okay, so we'll do that on Friday, but let's get started on IR spectroscopy. All right, So that's the NMR. We went very, very slow on NMR spectroscopy. We started from the theoretical background. We then started talking about what are the information you can get by looking at NMR spectroscopy. It's one of the most important spectroscopy tools you have. But on top of NMR, we have other spectroscopy tools that can help us to expedite the process of solving the NMR spectrum. So IR spectroscopy is one of them, and will be very helpful for us to identify functional groups in our organic molecules. And once you know the functional group, it becomes easier to derive information from your NMR spectroscopy. All right, so IR spectroscopy or infrared spectroscopy. The structure will be similar. We'll start by talking about the theoretical background and what are the assumptions we're making when we're talking about the infrared spectroscopy. And then we'll look at what are the information we can get in an IR spectroscopy, and then we'll do some case study. And we'll probably just end our IR spectroscopy. So your midterm will only cover everything after midterm 1 all the way to IR spectroscopy. We'll save the mass spectrometry and also solving complicated molecules with multiple spectroscopy method after your midterm 2. Okay, nevertheless, yes?
So is it like everything and not IR spectroscopy or IR spectroscopy?
We'll talk about it on Friday on what's being covered on midterm 2. Okay, so let's get started. Again, I say this is a review, but raise your hand if you never heard the term Born-Oppenheimer approximation. Okay, so we'll just pretend it is a review, but here's the approximation that we're making when we're talking about spectroscopy and why we can talk about spectroscopy. So in quantum mechanics, we have been covered quantum mechanics to describe electrons in the quantum mechanics picture, right? By solving the Schrödinger equation, you can get the probability of finding the electron somewhere in space. But in reality, not only electrons are acting as particles, your nuclei are also particles. We just covered NMR. We know your nuclei also have spin. So how can we solve it if your nuclei and the electrons are entangled to each other? So Born-Oppenheimer approximation is one of the fundamental approximations we made so that we can use spectroscopy independently from the electronic wave function. So here's the idea behind the Born-Oppenheimer approximation. What it says is just say the motions of the nuclei and the electrons in a molecule can be treated separately. All right, so that's the definition of Born-Oppenheimer approximation. What does it actually mean? As you can imagine, 2 different scenarios. Now we know that in a molecule, your electrons have much faster speed comparing to your nuclei. So what does that mean? It means that if we're in the point of view of the electron, like imagine yourself is moving really, really fast, and you're looking at something that's not moving as fast as you are. Like you're in an airplane, and you're looking at something on the ground, like a person walking. So in your eye, or in the eye of the electrons, your nuclei are pretty much fixed. So that gives us the possibility of solving the electronic wave function for the electrons, assuming my nuclei are not moving. At the same time, now we know my electrons are moving so fast comparing to the nuclei. So in the point of view of the nuclei, the electrons are just delocalized everywhere. It's no longer a fixed particle or anything. So what does that mean is in the point of view of the nuclei, it's seeing the electrons surrounding it as a delocalized potential. So what that means is we can just treat the electrons as a delocalized potential without need to worry about the specific wave function of the electron when we're focusing on the motion of the nuclei. When we're saying motion of the nuclei, we're talking about measurement of bond length, bond angle, stretching mode, normal mode, etc. So Born-Oppenheimer approximation is one of the fundamental approximations we made, so we can use spectroscopy to probe what are the motions of my nuclei. All right. So Again, in spectroscopy, we've seen this before. When we're talking about spectroscopy, we're talking about your molecule is absorbing light. And that absorption of the light can cause excitation of the molecule from two different quantum states. So in the UV-vis absorption spectroscopy, we're talking about the movement of the electron from the HOMO to the LUMO. So that is excitation of electronic state. In our NMR spectroscopy, we're talking about the different spin states of your proton nuclei, right? So then we're talking about the movement between the lower lying spin state to the higher lying spin state. So in spectroscopy, whatever we're measuring, it depends on the wavelength of the light you're using. We're always talking about an initial state and a final state. And by absorption of light, absorption of energy in that light, you're switching from the initial state to a higher lying final state. And spectroscopy tells us information about the delta E between that initial state and final state. So depending on what kind of wavelength you're getting, you can get different kind of states we're interested in. It can be an electronic state, can be spin state, or when we're talking about infrared spectroscopy, we're talking about vibrational state. Or if we're looking at a bit more detail, is in our diatomic molecule, your energy total have 4 different parts, if you may. You have the electronic energy. So this part of energy we're talking about in the UV-vis absorption, you're exciting your molecule, you're exciting the electron in your HOMO to the LUMO. So that's the electronic state of your molecule. And then you can have vibrational states. So that's, say, now we have 2 atoms, they're vibrating, and we're talking about different vibrational states. You have rotational states, so you can imagine your bond now is like in my Apple Pencil, and I'm just rotating it around. And that rotational state is also quantized. And then we have translational states. So in here, the top one, the electronic state, is talking about the energy state of the electrons, like HOMO, LUMO, pi correlation diagram, that's the UV-vis. And these are motions of the nuclei. And again, depending on what kind of wavelength we're using, we can excite different quantum states. So as a quick summary, I'll give you the table. These are the table of spectroscopy chemists typically use in organic chemistry. And we covered some of them, and some of them we won't be able to cover, but I just want to show you the entire table. So what we have on the left, we have the wavelength. So the way we organize this table is we start from low energy wavelengths all the way to high energy wavelengths. And wavelength tells you what kind of laser that is. Like a low energy wave is like a radio wave. A higher energy wave would be like X-ray. And it can excite different kinds of quantum states in your molecule. And it gives you different kind of molecular information. So for example, the first one, excitation of the nuclear spin, that is the NMR we were talking about. And remember, we're using radio wave to get the NMR, and it gives us information like bonding environment, molecular structure. We spent almost 3 lectures on talking about NMR before. Also, at the same time, we have been talking about the UV-vis spectroscopy. So remember UV-vis, now we're increasing the energy level of the laser we're using. We're using more higher energy level to excite my valence electrons, right? We're moving the electrons from the HOMO to the LUMO. We're talking about excitation of my electronic states. So it has higher energy, it tells us information about what are the electronic energy levels. And in between here, we have our IR spectroscopy. So it is IR spectroscopy, so judging by its name, infrared. So the wavelengths we're using are in the infrared region, so that's the wavelengths we're using. And it gives us information of vibrational energy. All right. We have four more minutes, so I'm just going to quickly introduce what does vibrational energy mean, and we'll pick up on Friday in where we left over. So when we're talking about vibrational excitation, the way to think about it is this is a harmonic oscillator, or the other way to put it is now you have two balls that's attached on a spring. So one of the common misunderstanding of organic molecules is they look just like static, they're not moving around. But in reality, your organic molecules are always moving around. It's always vibrating or like stretching or bending in some way. And the chemical bond in between the two atoms, you can imagine it as a little spring. And because it is a little spring, we can use the Hooke's law to rationalize what are these vibrational energy states. So you can imagine you have two little balls attached to the same spring, and we're using the Hooke's law to rationalize what that looks like. So in here, in Hooke's law, we have, well, several different terms. We'll just look at the left side. I have 3 more minutes, so we'll look at the wave number one. So this one is called the wave number. It's defined to be 1 over lambda. So that's the common unit we use in spectroscopy for frequency. The unit of your wave number is in cm minus 1. Or in the other word to say, it's one wave number is about 30 times 10 to the 9 hertz. It's just a way we try to rationalize what the wave number looks like, what the frequency looks like. And in this equation, K is a constant, F is a force constant, or the stiffness of your chemical bond, or how easy or how hard it is if you want to compress that spring. Mu here is the reduced mass, and we'll talk more about what each term means and how do they apply to chemistry in our next lecture. So in short, infrared spectroscopy, we use it to identify functional groups, and we'll see how to apply that in our next lecture. All right, thank you for your attention. See you on Friday.